In the warm, dusty air of an ancient Greek blacksmith's shop, a moment of profound discovery unfolded, one that would echo through the centuries and shape our quest to understand the cosmos. The story goes that the philosopher Pythagoras, walking past the workshop, was struck not by the heat or the noise, but by the distinct musical tones emanating from the hammers as they struck the anvils. His curiosity ignited, he rushed inside to investigate. What he found was not magic, but mathematics. The hammers that produced consonant, pleasing intervals, the perfect fourth, the perfect fifth, had masses that were in simple whole number ratios. A hammer twice as heavy as another produced a note exactly an octave lower. The harmony was not in the material or the force, but in the proportion. This was a revelation of the highest order. For Pythagoras and his followers, this was a glimpse into a hidden divine order. They believed that number was the fundamental reality underlying all things, and that the same mathematical relationships governing the harmonious sounds on Earth must also govern the motion of the celestial bodies. If simple ratios created beauty in music, then surely the magnificent, orderly dance of the planets, the moon, and the sun must be governed by a similar, though grander principle. They envisioned the cosmos as a series of crystalline spheres, each carrying a celestial body, nested within one another and rotating around the central Earth. The friction of these spheres moving against one another, they reasoned, must produce a sound, a sublime, ethereal hum. This was the birth of the concept of the music of the spheres, or musica universalis. It was not a metaphor. The Pythagoreans believed this cosmic music was a real, physical phenomenon, a continuous heavenly harmony produced by the motion of the heavens themselves. Yet, there was a profound paradox at the heart of this belief. Why, if this music was real, could no one hear it? Their answer was as elegant as it was untestable. This music was so constant, so ever-present from the moment of our birth, that our senses had become deaf to it. It was the sonic equivalent of the air we breathe, so fundamental to existence that we notice it only by its absence. To hear it would be to achieve a state of perfect philosophical purity, to transcend ordinary human perception and attune one's soul directly to the mathematics of creation. This idea was more than just a quaint musical theory. It was a complete philosophical system that linked the macrocosm of the universe to the microcosm of the human soul. They saw a direct correspondence between the celestial harmony and the internal harmony of a well-ordered life. Just as the planets moved in perfect mathematical accord, so too should a person strive to bring their passions and intellect into a balanced, harmonious state. This internal harmony was, in their view, the very foundation of health and virtue. The silent music was not just out there in the sky. It was a potential state of being within oneself. The legacy of this ancient intuition is immense. It established a powerful and enduring precedent. The universe is not chaotic but orderly. Its workings can be understood through mathematics. This faith in a rational mathematical structure to reality is the bedrock upon which all of modern science is built. From the orbits of planets described by Kepler's laws to the fundamental forces described by equations. We are the heirs of the Pythagorean belief that nature's book is written in the language of mathematics. Yet, for nearly 2 millennia, the literal music remained a beautiful, unproven poem. The vision of singing crystalline spheres could not survive the revelations of Copernicus, Galileo, and Newton. We learned that space is a vacuum, incapable of carrying sound waves. The planets do not move on physical spheres, but in elliptical orbits through empty space, held by an invisible force called gravity. The literal interpretation of the music of the spheres was silenced by cold, hard fact. The symphony, it seemed, had been cancelled. The ancient intuition appeared to be a beautiful but ultimately false dream. But as we will see, this was not the end of the story. It was merely the end of the first movement. The dream was not wrong. It was premature. The cosmos was not silent. We were simply listening for the wrong kind of music, in the wrong medium with the wrong ears. The Pythagoreans had correctly sensed the vibration at the heart of reality. But it would take us 2,000 years to build the instruments capable of hearing its true, spectacular, and silent song. The Pythagorean dream of a mathematical cosmos never truly died. It merely slept, waiting for a mind with both the poetic soul to hear its melody and the scientific rigor to calculate its notes. That mind belonged to Johannes Kepler, a man straddling 2 worlds. the mystical, symbolic universe of the Renaissance and the emerging data-driven world of modern science. Inheriting the precise, voluminous astronomical observations of Tycho Brahe, Kepler sought not just to describe planetary motion, but to understand its divine architecture. He was convinced that God, the great geometer, had composed the solar system according to a harmonic plan, and he intended to find the sheet music. Kepler's quest was detailed in his 1619 work, Harmonices Mundi, the Harmony of the World. In it, he attempted to translate the celestial dance into a literal, albeit inaudible, symphony. His approach was far more sophisticated than the simple spheres of the Pythagoreans. He had his 3 laws of planetary motion, which described the elegant ellipses and varying speeds of the planets. It was from this very motion that he extracted his music. First, he assigned each planet a musical note based on its maximum and minimum orbital speeds. As a planet orbits the Sun, it does not move at a constant speed. It moves fastest at its closest approach, perihelion, and slowest at its farthest point, aphelion. Kepler interpreted this changing angular velocity as a changing pitch. The slowest speed represented the lowest note in a planet's range, and the highest speed represented its highest note. For example, Saturn, the slowest and most ponderous planet, sang a deep, lugubrious bass, its range spanning just a minor third. The Earth, in contrast, sang a slightly wider interval, a plaintive semitone from mi to fa, which Kepler somberly interpreted as misery and famine. Mercury, zipping around the Sun at a frantic pace, had the widest vocal range of all, a dazzling octave and a half. But a melody needs a rhythm, and here Kepler's genius found its most profound expression. He realized that the different planets completed their orbits in different times. Their year was their fundamental rhythm. He sought the harmonic ratios between these planetary periods. He compared the extreme angular velocities of different planets, looking for the same simple, consonant ratios that please the ear in music: the octave 2-1, the fifth 3-2, the fourth 4-3. To his transcendent joy, he found them. He documented what he called a divine duet between Jupiter and Saturn. At their closest approach, their maximum and minimum speeds formed near-perfect musical intervals. It was as if at key moments in their great celestial dance, these giant worlds sang in harmony. This was the core of his celestial music. Not a continuous melody, but a grand polyphonic motet where the planets, like individual singers in a choir, only sounded their specific notes at precise points in their orbits, creating a slow, stately harmony that unfolded over centuries. The solar system was a colossal, intricate music box, playing a piece of unimaginable length and complexity. The ultimate expression of this harmony was Kepler's 3rd law, which he discovered while writing this very book. The law states that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This was not just a dry mathematical formula to him. It was the fundamental chord that held his symphony together. It was the unifying principle that linked the rhythms of the planets, their periods, with their positions in the cosmic scale, their distances. It was the grand underlying rule of composition for the entire solar system. Yet for all its mathematical brilliance, Kepler's symphony was, like the Pythagoreans, a silent one. He knew this. He wrote that this music is not conceived to be sounded by the ears, but by the intellect, an intellectual music, perceivable only in the mind. It was a music of geometry, of angular velocity, of divine proportion. He had not found a physical vibration in a medium, but a deeper, more abstract harmony written into the very laws of motion. Kepler's work represents the last great attempt to describe the cosmos in overtly musical terms, and the first to ground that music in precise empirical data. He was a bridge. He began with a mystical dream of celestial song, and in his pursuit of it, uncovered one of the most fundamental physical laws of the universe. He failed to find the literal music of the spheres, but in that very failure he succeeded in revealing a cosmos that was even more magnificently ordered than anyone had imagined. The music was not in the sound, but in the sublime mathematical structure itself. The score was not written on a staff, but in the elliptical orbits and harmonic ratios of planetary motion. The symphony was silent, but its notation was now for the first time laid bare for all to see. The grand symphonies of Pythagoras and Kepler were among the most beautiful ideas ever conceived by the human mind. They offered a universe that was not only intelligible, but also beautiful, a cosmos vibrating with a hidden mathematical music that connected the motion of the heavens to the harmony of the human soul. It was a vision of profound meaning and order. But the march of science is often a cold one, and this beautiful idea was destined to collide with a stark, unyielding physical reality, the vacuum of space. The demise began not with a bang, but with a gradual creeping realization about the nature of the world above our heads. For centuries, the Aristotelian view held sway that the heavens were filled with a perfect fifth element, the ether, a substance that could plausibly carry the celestial vibrations. But as the scientific revolution gained momentum, this comforting picture began to unravel. The telescope, that great revealer of cosmic truth, played a pivotal role. When Galileo pointed his spyglass at the heavens, he did not see smooth, crystalline spheres. He saw a jagged, imperfect lunar surface pockmarked with craters and scarred by mountains. He discovered moons orbiting Jupiter, a clear violation of the idea that all celestial bodies were fixed to their own unique rotating spheres. The heavens were not a realm of perfect, immutable objects. They were a place of complex, independent bodies moving through void. The final logical blow was delivered by Isaac Newton. His law of universal gravitation provided a powerful, mathematical description of planetary motion that required no physical spheres. Gravity, he proposed, was a force that could act across vast, empty distances. This concept of action at a distance was deeply troubling to many, but it worked with breathtaking precision. The planets were not embedded in spinning crystal. They were falling perpetually, in a graceful ballet choreographed by an invisible force through an immense and soundless nothing. And that nothing was the key. Sound, as we understand it, is a mechanical wave. It is a vibration that requires a medium to propagate, a substance whose atoms can be compressed and rarefied, passing the energy of the disturbance along. In air, it is the countless collisions of nitrogen and oxygen molecules. In water, it is the jostling of water molecules. But in the vacuum of space, there is nothing, or so close to nothing that it makes no difference. There are no atoms to bump into their neighbors, no medium to compress. A vibration there is like a clapper without a bell. The motion occurs, but it creates no sound. The most colossal explosion in the universe, a supernova, would unfold in absolute terrifying silence to a nearby observer, the visible fury of expanding gas accompanied by no roar, no rumble, only the mute dance of light. This understanding drained the music of the spheres of its literal meaning. Kepler's Divine Motet, with its bass Saturn and soprano Mercury, was a composition that could never be heard. The planets, for all their majestic speed, were silent runners on a track of nothingness. The beautiful ratios and harmonies he had discovered were not the notes of a symphony, but the abstract kinematic parameters of orbital mechanics. The music was a metaphor, a poetic description of mathematical relationships, not a physical phenomenon. This was the death of a beautiful idea. The cosmos was not a great resonating instrument. It was a cold, dark, and mostly empty void, punctuated by isolated islands of matter. The romantic notion that we were living inside a divine concert hall was replaced by the chilling image of being adrift in a silent, airless ocean. The universe, it seemed, was not only indifferent, but it was also mute. For a time, this felt like a profound loss, a demotion from a universe rich with meaning to one of sterile mechanism. The dream of the spheres was a casualty of our growing up, a necessary but painful step in trading a comforting myth for a more accurate, if less enchanting, reality. The silence of space became the new paradigm, a fact so fundamental it was drilled into every student of science. In space, no one can hear you scream. Yet this death was not an end, but a transformation. By killing the literal physical music, science forced the idea to evolve. The human desire to find harmony in the cosmos did not vanish. It simply had to look for a different kind of music. The question shifted. If the universe was not making sound, was it perhaps vibrating in another way? If there was no ether to carry waves of pressure, was there another, more subtle medium that could? The dream of the spheres did not die. It went underground, waiting for a new physics and a new kind of listening. The silence was not the end of the song, but the pause before a far stranger and more revolutionary movement began. The death of the literal music of the spheres left the cosmos silent, but it also left it waiting. The ancient intuition that the universe was fundamentally dynamic and vibrational was too powerful to simply vanish. It lingered, a ghost in the machine of physics until a quiet revolution in the early 20th century provided a new medium, a new instrument, and a new kind of wave. The conductor of this revolution was Albert Einstein, and his new composition was titled General Relativity. Einstein's great insight was to dismantle the Newtonian stage. For Newton, space was a static, absolute, and immutable background, a rigid grid against which the drama of moving matter played out. Gravity was a mysterious force that somehow reached across this empty grid to pull objects together. Einstein proposed something far more radical. He suggested that space and time were not separate, passive entities but were woven together into a single, four-dimensional fabric. Space-time. And this fabric was not rigid. It was dynamic, flexible, and responsive. The key to this new vision was the relationship between matter and space-time. Einstein's field equations famously declared that matter and energy tell space-time how to curve. A massive object like the sun does not simply sit in space. It creates a deep four-dimensional dimple in the space-time fabric around it, and this curvature in turn tells matter how to move. The Earth is not being pulled by a mysterious force from the sun. It is simply following the most natural, straightest possible path, a geodesic, through the curved geometry created by the sun's mass. It is like a marble rolling in a curved bowl. The marble moves the way it does because of the shape of the bowl itself. This was the new medium. Space-time was not the old ether. It was not a substance made of particles that you could touch or measure the density of. It was the underlying geometry of reality itself. And if this fabric could be curved, Einstein's equations also revealed something astonishing. It could also ripple. Imagine the cosmic fabric as a vast, taut trampoline. If you place a heavy bowling ball in the center, it creates a steady, deep indentation. This is like the sun warping space-time. Now imagine taking two other bowling balls and spinning them rapidly around each other on this trampoline. Their violent, accelerating motion would not just create stationary dips. It would send waves, vibrations, racing outward across the fabric. These are gravitational waves. In Einstein's universe, any mass that accelerates, that changes its speed or direction, disturbs the space-time around it, generating ripples that propagate outward at the speed of light. These are not waves in space. They are waves of space itself. As a gravitational wave passes through a region of space, it literally and minutely stretches and squeezes the fabric of space-time itself, alternately compressing and expanding distances in directions perpendicular to its travel. This was the rebirth of the cosmic music, but in a form the ancients could never have conceived. The medium was not a material substance but the geometry of the cosmos. The sound was not a vibration of atoms but a vibration of reality's very foundation. The most powerful sources of these waves are the most violent events in the universe, the cataclysmic mergers of black holes and neutron stars. These events are the cosmic equivalents of a colossal drumstick striking the space-time drum. There was, however, a profound catch. The stiffness of space-time is unimaginably immense. The gravitational force may seem weak to us, but that is only because it takes an enormous amount of energy to warp the fabric of the universe. Consequently, the ripples produced by even the most colossal cosmic events are infinitesimally small. A gravitational wave from a distant black hole merger, after traveling 1 billion light-years, might change the distance between two objects by less than the width of an atomic nucleus. Detecting such a wave seemed for decades to be a practical impossibility. Yet, the theoretical revelation was complete. Einstein had provided the new score for the music of the spheres. The universe was not silent after all. It was filled with a silent symphony of space-time vibrations, a cacophony of inaudible waves generated by orbiting pulsars, colliding galaxies, and the remnant echo of the Big Bang itself. The music had not vanished. It had simply shifted to a register so deep and required a medium so fundamental that we had been utterly deaf to it. We had been listening for a melody in the wind, while the entire Earth was humming a bass note of unimaginable depth. The challenge was no longer to prove the music existed in theory, but to build an ear delicate enough and patient enough to finally hear it. If the gravitational waves from colliding black holes are the complex modern symphonies of the cosmos, then the cosmic microwave background is its first fundamental chord. It is the earliest music we can ever hear, a fossilized vibration from the dawn of time that still reverberates through the universe today. But to understand this chord, We must journey back to a time when the universe was not transparent and dark, but a searing, opaque plasma, and where sound was not a traveler in space, but the very mechanism shaping it. For the first 380,000 years of its existence, the universe was a dense, seething soup of particles and energy. Protons, electrons, and photons were locked in a violent, intimate dance. The photons, particles of light, could not travel freely. They would zip a short distance before being scattered, absorbed, and re-emitted by a free electron. The universe was a brilliant, impenetrable fog. But within this fog, a cosmic battle was raging, and its weapon was sound. This battle was between two titanic forces, gravity and radiation pressure. Gravity, acting on the faintest of quantum seeds from the Big Bang, tirelessly tried to pull the primordial gas inward, creating regions of slightly higher density. But the intense pressure of the trapped radiation, the photons, fought back, pushing outward against this gravitational collapse. This created a push-pull effect, a continuous oscillation. A pocket of gas would begin to collapse under gravity, compressing the plasma and photons within it. This compression would increase the radiation pressure until it became so strong, it would overcome gravity and blast the material outward. As the pocket expanded and rarefied, gravity would once again gain the upper hand, pulling it back in. The result was a spherical sound wave, a ripple of compression and rarefaction, radiating outward through the hot plasma. The entire early universe was a roaring ocean of these spherical sound waves, overlapping and interfering with one another. The cosmos was ringing like a bell. The fundamental note of this bell was determined by a single factor: how far sound could travel in the time before the music stopped. This distance, the sonic horizon, became the universe's first and most important standard ruler. Then, a momentous transition occurred. As the universe expanded, it cooled. Around the 380,000-year mark, the temperature dropped enough for electrons to be captured by protons, forming the first stable, neutral hydrogen atoms. In an instant, the fog lifted. The photons, which had been trapped for eons, were suddenly set free. They burst outward in every direction, and the universe became transparent. This event is called recombination, and the flash of light released is what we detect today as the cosmic microwave background. But this light did not just carry a snapshot of temperature, it carried a snapshot of that final frozen moment of sound. The CMB is not a uniform glow. It is mottled with tiny variations, hot spots and cold spots that differ in temperature by mere millionths of a degree. These spots are not random. They are the direct imprint of those primordial sound waves at the exact moment the music stopped. A region that was in the compressed, dense phase of a sound wave was slightly hotter and appears as a hot spot in the CMB. A region that was in the expanded, rarefied phase was slightly cooler and appears as a cold spot. The most common size for these spots corresponds precisely to the scale of the sonic horizon, the farthest a sound wave could have traveled by that time. It is the fossilized crest of the most fundamental wave the universe ever produced. When cosmologists analyze the pattern of these hot and cold spots, they perform a kind of statistical symphony analysis, creating what is known as a power spectrum. This spectrum shows a series of distinct peaks, and the first peak is the loudest and most fundamental. It is the resonant frequency of the cosmic bell, the clear, dominant note of that first chord. The subsequent peaks are harmonics, providing a richer, more complex sound that tells us about the composition of the early universe, the ratio of ordinary matter to dark matter, the density of the cosmos, and its geometry. This first chord, this CMB, is the foundational note upon which the entire cosmic symphony was built. Those tiny frozen ripples of density were the gravitational seeds for everything that followed. The slightly denser regions revealed as slightly cooler spots would, over hundreds of millions of years, pull in more and more dark matter and gas. They would collapse under their own gravity to form the first stars, the first galaxies, and the vast web-like structure of the modern universe. So, when we look at a map of the cosmic microwave background, we are not just looking at a baby picture of the universe. We are looking at its first and most important musical score. We are seeing the fundamental chord from which all structure, every galaxy, every star, every planet would eventually grow. It is the silent, fossilized echo of the universe's first and greatest performance. A single resonant chord struck at the dawn of time, whose vibrations set in motion the creation of everything we see. The map of the cosmic microwave background is the universe's opening chord, But it is also something more, a fossilized recording of a specific, universal rhythm. That rhythm has a name, baryon acoustic oscillations, and it represents the fundamental repeating beat against which the entire large-scale structure of the cosmos has been built. It is the universe's bass note, a cosmic drum that beat only for a brief moment in time, but whose echo can still be found imprinted on the distribution of galaxies today. To understand this, we must return to the early universe's plasma, that hot soup where ordinary matter, baryons, protons and neutrons, and light photons were locked together. As we've seen, gravity would try to collapse a dense patch of this plasma, but the photons, exerting immense radiation pressure, would fight back, creating an outward-moving spherical sound wave, a shell of compressed plasma and photons expanding from the initial seed. This was not a single event, but the dominant rhythm of the young cosmos happening everywhere at once. This oscillation had a specific fundamental scale, the sound horizon. This was the maximum distance a sound wave could travel from the Big Bang until the moment of recombination, when the universe cooled and atoms formed. When this happened, the music stopped abruptly. The photons, which had provided the outward pressure, decoupled from the matter and streamed away, becoming the CMB. The baryons, suddenly devoid of their photon pressure, were left stranded. They were frozen in place at the outer crest of that final sound wave, like sea foam left on a beach after a wave recedes. This process created a cosmic signature with two components. At the center of each of these vast spherical sound waves was the original gravitational seed, now enriched with a large amount of dark matter, which had been unaffected by the photon pressure and simply continued to clump at the center. And surrounding this central overdensity was a single spherical shell of ordinary matter, the stranded baryons. The radius of this shell was exactly the sound horizon size. This is the pattern we see frozen into the CMB. The hot and cold spots are the imprints of these shells in their centers. But the story doesn't end there. This fossilized rhythm did not vanish. It was imprinted not only on the light, but on the very distribution of matter itself. After recombination, the universe entered the dark ages, and then the first stars and galaxies began to form. They did not form randomly. They formed preferentially in the regions of highest density, the gravitational seeds that had been laid down by the acoustic oscillations. This means that the large-scale structure of the universe today, the vast cosmic web of galaxies and clusters separated by great voids, inherits its fundamental spacing from that primordial rhythm. Imagine a vast, silent drumhead that was struck once long ago. The drumhead vibrated, creating a standing wave with a specific distance between its peaks and troughs. Then the drumhead instantly froze solid, preserving that wave pattern. Now imagine that fireflies are only born at the peaks of those frozen waves. If you mapped the positions of all the fireflies, you would see that they are not scattered randomly. They are preferentially separated by the wavelength of that original drumbeat. This is what astronomers do when they create massive three-dimensional maps of millions of galaxies. They don't just see a random scatter. They detect a slight statistical preference for galaxies to be separated by a specific scale, about 500 million light-years. This is not the size of the sound horizon today. The universe's expansion has stretched that original scale, just as it stretched the CMB light. This measured scale is the grown-up stretched version of the universe's first and only rhythm. This makes baryon acoustic oscillations one of the most powerful tools in modern cosmology. It is a standard ruler, etched into the fabric of the cosmos. By measuring the apparent size of this ruler at different epochs in the universe's history, from the CMB to the distribution of ancient galaxies to the map of relatively nearby galaxies, we can trace how the expansion of the universe has evolved over billions of years. This provides one of the most robust and independent confirmations of the existence of dark energy, the mysterious force accelerating this expansion. The BAO signal is the universe's metronome. It is a faint, persistent rhythm that began with a thunderous chord in the hot plasma, was frozen into the CMB, and now whispers to us from the spatial arrangement of every galaxy in the sky. It is the fundamental beat that underlies the cosmic symphony, a constant, reliable pulse that allows us to measure the tempo of the universe's expansion and confirm that the cosmos is not just expanding, but its dance is getting faster and faster, driven by a mysterious dark energy. If the primordial sound waves of the early universe were its opening chord, and the baryon acoustic oscillations its underlying rhythm, then the entities that provide the cosmic drum solos, the spectacular, explosive beats that punctuate the symphony, are black holes. But not just any black holes. We are talking about the supermassive titans that reside at the centers of galaxies, and the spectacular, violent duets they perform when their galaxies collide. These events are the most powerful since the Big Bang itself, and they do not just create light or sound. They make the very fabric of space-time ring like a bell. To understand this, we must first abandon any notion of black holes as simple, cosmic vacuum cleaners. They are, in the language of physics, the simplest and most perfect objects in the universe, described only by their mass, spin, and electric charge. When two galaxies merge over billions of years, their central supermassive black holes are drawn together, eventually forming a binary pair. They begin a slow, intimate dance, orbiting one another in the dark heart of the new combined galaxy. As they orbit, they steal orbital energy from surrounding stars and gas, spiraling ever closer. This is a slow, stately process, but when they reach a critical separation of a few hundredths of a light year, a new and spectacularly efficient process takes over: the emission of gravitational waves. According to Einstein's theory, these two incredibly massive, accelerating objects begin to violently churn the spacetime around them. They are no longer just two objects in space. They are two dancers whose every step warps the very dance floor beneath them, sending out ripples. The final moments of this dance are the drum stroke. The black holes enter their final, frantic inspiral, orbiting thousands of times per second. The gravitational waves they emit become louder and higher in frequency, producing the now famous chirp signal. Then, in a fraction of a second, they merge. The event is one of almost unimaginable violence. The new single black hole that forms is initially born misshapen. It is not a perfect sphere, but a lumpy, vibrating entity. Like a struck bell, it must settle down, and it does so by shaking off its deformities in the form of a final, intense burst of gravitational waves. This is the ring down, the fading echo of the strike. The power of this event is beyond human comprehension. For that brief moment, the energy radiated in gravitational waves can outshine the combined light of every star in every galaxy in the observable universe. They are, quite literally, the loudest events we can ever detect. The frequencies of these waves, however, are far below what human ears could hear. If we could hear them, the merger of two stellar mass black holes would be a quick, high-frequency chirp. The merger of two supermassive black holes would be a deep, resonant, and earth-shattering bass note. A single, monumental beat that would last for minutes or even hours, shaking the very structure of reality. But we don't need to hear them to prove they are real. The detection of these waves by LIGO and Virgo from stellar mass black holes was the direct proof. For supermassive black holes, the waves are too low frequency for current ground-based detectors, but they are the primary target for a future space-based observatory like LISA, Laser Interferometer Space Antenna. Furthermore, the combined rumble of all the supermassive black hole mergers throughout cosmic history creates a persistent, low-frequency hum known as the gravitational wave background, a static hiss that is the integrated percussion section of the entire cosmos, which we are now on the verge of detecting with pulsar timing arrays. These cosmic drummers do more than just make noise. Their gravitational waves are a new form of astronomy. By listening to the chirp and ring down, we can learn the masses and spins of the black holes, properties that are often invisible to traditional telescopes. They are the only way to directly probe these dark fundamental engines that govern the evolution of galaxies. The supermassive black hole is the universe's ultimate percussionist. It is an instrument that plays not on air, but on spacetime itself. Its performance is one of pure, violent geometry, a testament to a universe that is not static and silent, but dynamic and vibrantly loud in a dimension we are only just beginning to perceive. In the silent void, where no sound can travel, the most massive objects in existence are beating out a rhythm on the drumhead of reality, and we have finally begun to feel the vibrations. For nearly a century, gravitational waves were a ghost in the machine of physics, a beautiful mathematical prediction of Einstein's theory, but one he himself thought might be forever undetectable. The universe was playing its symphony of space-time vibrations, but we were deaf to it. The challenge was not one of theory, but of almost unimaginable engineering. To hear this cosmic music, we had to build an ear of epic proportions and sensitivity. This is the story of the Laser Interferometer Gravitational Wave Observatory, or LIGO, the machine that gave humanity a new sense. The principle behind LIGO is elegant in theory, but Herculean in execution. It is based on a Michelson interferometer, the same type of device used in the failed hunt for the ether wind, but where Michelson's instrument was precise enough to measure the hypothetical effect of a planet moving through space, LIGO needed to be sensitive enough to measure changes in distance 10,000 times smaller than a proton. Its target was the stretching and squeezing of space-time itself as a gravitational wave passed through the Earth. To achieve this, LIGO couldn't be a tabletop experiment. It had to become a cathedral of precision. 2 facilities were built, separated by 165 miles in Livingston, Louisiana and Hanford, Washington. This separation was crucial to rule out local false alarms like minor earthquakes or a truck rumbling on a distant road. A real gravitational wave would sweep through both locations at the speed of light. At the heart of each facility are 2 arms, each 4 kilometers long, arranged in a perfect L. Down these staggering ultra-high vacuum tunnels, scientists fire a powerful laser beam. The beam is split at the corner, with each half traveling down an arm to a mirror suspended at the end. In normal conditions, when the light beams bounce back and recombine, they are tuned to cancel each other out through destructive interference. The result is darkness at the photodetector. But when a gravitational wave passes through, it briefly distorts space-time. It will stretch one arm by an infinitesimal amount, while simultaneously squeezing the other. This change in length, smaller than the width of a proton, alters the travel time of the laser light in each arm. The 2 light beams return to the corner ever so slightly out of sync. Their perfect dark cancellation is broken, and a flicker of light, a signal, is born. Building this was a war against noise. Every vibration of the Earth was an enemy. The mirrors, weighing 40 kilograms each, are suspended by fused silica fibers, a pendulum system so isolated it is effectively shielded from the rumble of the world. They are some of the smoothest objects ever created, so perfect that if they were scaled to the width of North America, their largest imperfection would be the height of a pebble. The laser must be impossibly steady and pure. Even the random jostling of atoms in the mirror coatings, a phenomenon called quantum noise, threatens to drown out the whisper from the cosmos. For decades, the initial LIGO detectors listened and heard nothing but silence and terrestrial noise. It was a period of patient, relentless refinement. Then, from 2010 to 2015, the system underwent a monumental upgrade to become advanced LIGO. The lasers were made more powerful, the vibration isolation was made even more exquisite, and the mirrors were made heavier. The sensitivity was improved by a factor of 1,000. The new ear was open for business, listening more keenly than ever before. And then on September 14, 2015, just days after the upgraded detectors began their first official observing run, it happened. A signal, clear and strong, swept through both Livingston and Hanford within milliseconds of each other. It was a chirp, a rising frequency and amplitude that perfectly matched the theoretical prediction for the final inspiral and merger of 2 black holes, one 36 and the other 29 times the mass of our Sun, over 1 billion light-years away. The moment was one of stunned, historic disbelief. The data was so clean, so textbook perfect, that many on the team initially suspected it was a blind test, a hardware injection planted by the collaboration's own members to test the analysis pipeline. But it was real. For the first time, a gravitational wave had been directly detected. The ghost had been made flesh. With that single event, humanity crossed a threshold. We were no longer creatures of light alone. For all of history, our knowledge of the cosmos came from electromagnetic radiation, visible light, radio waves, X-rays. We were astronomers looking at the universe. With LIGO's success, we became listeners. We could now perceive the vibrations of space-time itself, a messenger that travels unimpeded through dust and gas and time, carrying stories from the darkest, most violent events in the cosmos. We had built an ear, and in doing so we had opened a new sense, tuning in to the silent, rhythmic drumming of the universe. For decades, the search for gravitational waves was a story of quiet persistence, of battling against unimaginably small signals and the ever-present roar of a noisy Earth. The LIGO detectors, freshly upgraded to their advanced configuration, were switched on in September 2015 for their first official engineering run. They were still being calibrated. The serious data taking wasn't scheduled to begin for another few days. The atmosphere was one of cautious optimism, a feeling that after years of work, they were finally getting close. No one was prepared for what happened next. At 09:50:45 Universal Time on September 14, 2015, a ripple in space-time, born from a cataclysm a billion light-years away, swept through the Earth. It passed through the detector in Livingston, Louisiana. 7 milliseconds later, having traveled at the speed of light, it reached the twin instrument in Hanford, Washington. In the control rooms, the data stream flickered. A signal appeared, so clear and strong it was visible to the naked eye, even before complex computer analysis. It was a sound that would change physics forever. The signal was a chirp. It began at a low frequency of 35 Hz, a deep rumble at the edge of human hearing. In less than a quarter of a second, it swept upwards in both frequency and amplitude, climbing to 250 Hz before culminating in a final, characteristic ring down. The entire event was breathtakingly brief, a cosmic blip that had traveled for a billion years to spend just 0.2 seconds in our detectors. But its shape was unmistakable. It was the precise fingerprint predicted by Einstein's equations for the final in-spiral, merger, and ring down of two massive black holes. The initial reaction among the scientists who saw it was not jubilation, but profound suspicion. The signal was too perfect. For a community hardened by years of null results and false alarms, the immediate assumption was that this was a blind injection, a sophisticated test where the collaboration's own members secretly inject a fake signal into the system to keep the data analysis teams on their toes and to test the entire detection pipeline from start to finish. It was a drill they had run before. An email went out to the collaboration's testing group. "We need to know right now if this is an injection." The response came back. No one in the group had authorized one. The suspicion deepened, turning to a slow-dawning, electrifying realization. If it wasn't a test and it wasn't a known source of noise, then there was only one possibility left. It was real. What they had witnessed was the death spiral of two black holes, one 36 times the mass of our sun, the other 29. For eons, they had orbited each other. In their final moments, they whirled around at half the speed of light, churning the space-time around them into a frenzy and radiating away their orbital energy in a torrent of gravitational waves. The peak of the merger, the moment the two horizons became one, released more power than the combined light of every star in the observable universe. In that instant, 3 solar masses of energy were converted directly into gravitational waves, according to Einstein's ERXMC2. The resulting single black hole, 62 times the mass of the sun, was left vibrating, settling into its new shape by shedding its deformities in the form of the final ring down. The event was given a name, GW1550-914. GW for gravitational wave, 15 for the year, 09 for the month, and 14 for the day. It was the first note ever recorded in the symphony of gravitational wave astronomy. The months that followed were a whirlwind of frantic, secretive work. The teams at LIGO, along with their partners at the Virgo detector in Europe, had to verify the data with obsessive rigor. They had to rule out every conceivable terrestrial or human cause, seismic activity, electrical glitches, even malicious hacking. Every check came back clean. The signal was cosmic. When the discovery was finally announced to the world on February 11, 2016, the scientific community erupted. It was not just the confirmation of a century-old prediction, it was the opening of a new window on the universe. We had not just seen the cosmos, we had felt its vibrations. We had heard the unmistakable sound of two invisible, cosmic ghosts colliding in the dark. The chirp of GW 914 was the first true note of the silent music of the spheres, a note played not on a material medium, but on the strings of space-time itself. It was the proof that the universe was not silent, but that we had finally, after centuries of dreaming, learned how to listen. The detection of GW 914 was a revolution, but it was a silent one. We had felt the tremor of colliding black holes but seen nothing. They were events of pure gravity, occurring in the darkest depths of space. The universe had given us a new sense, but it was as if we were only hearing one instrument in a vast, dark concert hall. That all changed on August 17, 2017, when the cosmos performed its first full multi-messenger symphony, an event that combined the feel of gravitational waves with the sight of light, revealing a spectacular and violent creative process. It began, as before, with a chirp. At 12:41:04 Universal Time, the LIGO detectors in the United States and the Virgo detector in Italy recorded a gravitational wave signal. But this one was different. It was not the brief sub-second thunderclap of massive black holes. This signal, named GW 170817, lasted for a full 100 seconds, a long, rising siren song in the fabric of space-time. Its frequency and characteristics pointed not to black holes, but to something less massive and far more complex: the final death spiral of two neutron stars. Neutron stars are the incredible, dense corpses of massive stars so compressed that a single teaspoon of their material would weigh billions of tons. As these two stellar corpses circled each other, they shredded each other with immense tidal forces, emitting a long, clear gravitational wave cry that signaled their impending doom. The precision of the three detectors allowed for a rough triangulation of the signal's origin, pointing to a broad patch of the southern sky. What happened next was an unprecedented moment in scientific history. Just 1.7 seconds after the gravitational wave signal ended, NASA's Fermi Gamma Ray Space Telescope, and independently the Integral satellite, detected a short gamma-ray burst from the exact same region of the sky. This was the spark. The gravitational wave was the rumble of the engine. The gamma-ray burst was the flash of the exhaust. For the first time, we had both felt and seen the same cataclysmic event. An alert went out to astronomers worldwide. The hunt was on. Telescopes of every kind, from giant radio dishes to optical behemoths to space-based X-ray and ultraviolet observatories, swung toward the location. A galaxy called NGC 4993, about 130 million light-years away. They were searching for the aftermath, the kilonova, and they found it. 11 hours after the initial detection, optical telescopes in Chile spotted a new, brilliant blue pinprick of light in that galaxy. It was the kilonova, the radioactive glow of material blasted into space during the neutron-star merger. As days turned to weeks, astronomers watched in awe as the color of this transient object shifted from blue to red, its light fading over time. They were witnessing the cosmic forge in action. The collision of two neutron stars is the universe's primary factory for the heaviest elements. In the intense pressure and density of the merger, raw nuclear material, mostly neutrons, is squeezed together, capturing neutrons in a frantic process called the Rapid Neutron Capture Process, or R process. This is how nature forges elements like gold, platinum, uranium, and plutonium. The expanding cloud of the kilonova is a cosmic cloud of radioactive waste, glowing with the light of these newly minted elements decaying. The data from the light confirmed what the gravitational waves had suggested. The event produced a cloud of gold with a mass perhaps hundreds of times that of the Earth, and platinum over 1,000 times our planet's mass. The wedding ring on your finger, the uranium in a power plant, the plutonium in a deep space probe, all were likely born in such a spectacular, violent collision billions of years ago. GW 170817 was the complete performance. The gravitational waves were the deep resonant bass note, telling us about the masses and dynamics of the dancers. The gamma-ray burst was the brilliant percussive crash of cymbals. The evolving light of the kilonova was the full orchestral swell, revealing the chemistry of creation. It was a symphony in 3 movements, perceived by 3 different senses. This single event transformed multi-messenger astronomy from a dream into a routine. It confirmed that neutron star mergers are the source of short gamma-ray bursts and the cosmic origin of the heaviest elements. It provided a new, direct way to measure the expansion rate of the universe. Most importantly, it proved that to truly understand the cosmos, we cannot just listen or just look. We must do both. We must feel the vibrations of space-time and see the resulting light, combining them to hear the full magnificent orchestra of the universe, and finally understand the music it is playing. The chirps from colliding black holes and neutron stars are the solos and crescendos of the cosmic symphony, loud, distinct, and impossible to ignore. But if you listen carefully to any great piece of music, beneath the prominent melodies there is often a deep, continuous hum, a foundational resonance that underpins everything. The universe has such a hum. It is the gravitational wave background, a faint, persistent static generated not by a single event, but by the combined rumble of all the merging supermassive black holes in the cosmos, a choir of giants singing in the lowest register imaginable. To understand this hum, we must shift our scale. The black hole mergers detected by LIGO and Virgo are of the stellar mass variety, typically weighing between a few and 100 times the mass of our Sun. Their collisions are brief, violent, and produce high-frequency gravitational waves. The gravitational wave background, however, is the domain of the true titans, supermassive black holes, millions to billions of times the mass of the Sun, which reside at the centers of galaxies. Throughout cosmic history, galaxies have frequently collided and merged. When they do, their central supermassive black holes are drawn together, eventually forming a binary pair. These binaries, spanning distances comparable to our solar system, orbit each other for millions of years before finally coalescing. Their immense mass and vast orbital scale mean they generate gravitational waves of incredibly low frequency, with periods of years or even decades. A single one of these waves would be too long and too faint for any terrestrial detector to isolate. But imagine every galaxy pair in the universe is doing this, each at a different stage of merger, each humming a slightly different note. The combined effect is a cacophony of low-frequency ripples that overlap into a steady, universe-filling background hum. It is the sound of the cosmic web itself, slowly settling and grinding through the eons. Detecting this hum required a different kind of ear, one far larger than any we could possibly build on Earth. The solution was to turn our sector of the galaxy into a colossal natural detector using pulsars. Pulsars are the rapidly spinning ultra-dense cores of dead stars, which beam radio waves outward with the metronomic precision of atomic clocks. They are nature's most perfect celestial lighthouses. The method, known as a pulsar timing array, works like this. Astronomers carefully monitor the arrival times of the pulses from an array of these stable, millisecond pulsars scattered across the sky. As a low-frequency gravitational wave, a ripple in spacetime, passes between Earth and a pulsar, it will minutely stretch and squeeze the path the radio waves have to travel. This causes the pulses to arrive at our telescopes ever so slightly early or late, in a correlated pattern across the sky. The effect is minuscule, distorting the timing of the pulses by mere 100 billionths of a second over a decade. It is like detecting a change in the length of a 1 light-year-long ruler by less than the width of a human hair. For over 15 years, consortia like the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, the European Pulsar Timing Array, and others have been patiently collecting this data, listening for this specific pattern in the chorus of the cosmos. In 2023, multiple teams announced they had found the first compelling evidence for this gravitational wave background. The data revealed the telltale signature, a low-frequency rumble, exactly as predicted, that grows stronger at lower frequencies, like the deep roar of a distant crowd. While the detection of the hum itself is a monumental achievement, its source is the next great mystery. The leading candidate is, as predicted, the population of orbiting supermassive black hole binaries. However, the hum's amplitude is surprisingly strong, suggesting these cosmic giants may be more common, merge more efficiently, or be more massive than we thought. But there are other, more exotic possibilities humming in this background. Some of this signal could be a relic from the very birth of the universe. Inflation, the period of faster-than-light expansion in the first instance after the Big Bang, could have created a primordial background of gravitational waves, a fossilized whisper from the dawn of time. Other theoretical contributors could be cosmic strings, hypothetical one-dimensional defects in spacetime, or phase transitions in the early universe. The hum is a new canvas, and we are only just beginning to decipher what is painted upon it. The gravitational wave background is the ultimate proof that the cosmos is never silent. It is a universe constantly in vibration. Beneath the dramatic soloists of Lego and Virgo, this deep, pervasive hum is the continuous soundtrack of cosmic evolution, the sound of galactic destiny unfolding over billions of years. We have moved from hearing the individual notes to perceiving the fundamental resonance of the universe itself, a bass note so deep it shakes the very foundations of space-time. We have listened to the echoes of the Big Bang and felt the tremors of colliding black holes. But the music of the cosmos is not only in these colossal singular events. It is also in the continuous, gentle hum of the stars themselves. Every star in the sky is a resonating instrument, a spherical bell ringing with a complex chorus of sound waves. The science of listening to these stellar vibrations is called Asteroseismology, and it allows us to perform the ultimate act of celestial diagnosis, seeing deep into the hidden hearts of stars by turning their flickering light into sound. To understand how a star sings, we must first recognize that a star is not a static, solid ball of fire. It is a vast, seething, and turbulent sphere of incandescent gas, a continuous nuclear furnace where immense energies are generated in the core and must fight their way to the surface. This churning convective motion, combined with the nuclear reactions themselves, acts like a continuous, random drumming on the star's interior. These countless tiny drum beats excite sound waves that travel through the stellar body. But a star is not a silent chamber. The density and temperature of the gas change dramatically from the incredibly dense hot core to the tenuous, cooler outer layers. This creates a complex, layered medium where sound waves will refract, reflect, and interfere. Certain frequencies will begin to resonate, just as specific frequencies will make a wine glass or a guitar string vibrate. These are the star's natural resonant frequencies, its unique acoustic signature. The entire star pulsates, rhythmically expanding and contracting, its surface rising and falling by tiny amounts as these standing waves course through it. We cannot hear this sound directly, of course. Space is a vacuum, and no sound travels to us, but we can see it. As the star pulsates, its surface moves. When the surface moves outward, it becomes slightly hotter and brighter. When it moves inward, it becomes slightly cooler and dimmer. These changes are infinitesimal, often a change in brightness of less than 1 part in 10,000. But with incredibly precise space telescopes like Kepler and TESS, we can detect them. We point our telescopes at a star and record its light with exquisite sensitivity. And what we get is not just a steady brightness, but a flicker. That flicker is the star's song, encoded in light. By applying sophisticated mathematical analysis, a process akin to figuring out the shape and size of a bell by listening to the note it rings, astroseismologists can decode this flickering light to reveal the star's deepest secrets. The frequencies of the oscillations tell us about the star's density. The spacing between certain frequencies reveals the age and evolutionary state of the star. It's like a stellar medical scan, allowing us to see the internal structure without ever touching it. For our own sun, this field, helioseismology, has given us a detailed ultrasound of its interior. We have mapped the differential rotation of its inner layers, located the boundaries of its convective zone, and even detected sunspots on the far side of the sun by listening to the waves that bounce through the core and emerge on the near side. We know the sun's composition, its age, and its internal temperature profile with remarkable precision, all from decoding the millions of resonant modes in which it vibrates. For distant stars, asteroseismology is even more powerful. Before this technique, estimating the age of a star was notoriously difficult. Now, by measuring the precise frequencies of its oscillations, we can determine its age with an accuracy of just a few %. This is crucial for understanding the evolution of planetary systems and the galaxy itself. When we discover planets orbiting a star, asteroseismology tells us the star's true size and mass with unparalleled accuracy, which in turn tells us the true size and orbit of the planets themselves. It separates the signal from the noise, the planet's transit from the star's own pulsations. When we translate these stellar light curves into sound, the result is a haunting, ethereal choir. Our own sun rings with a deep, low-frequency hum, a bass note from a giant. Smaller, denser stars produce higher-pitched, more rapid tones. A red giant star pulses with a slow, majestic rhythm, while a hot, young star might vibrate with a frantic, shimmering energy. Each star has its own voice, its own song dictated by its mass, age, and composition. The singing stars remind us that the music of the spheres is not a metaphor. It is a physical reality. Every star is a dynamic, vibrating entity, and its light carries the rhythm of its internal fire. Asteroseismology has given us the tuning fork to understand that rhythm, transforming the silent, twinkling points of light in our night sky into a grand, resonant orchestra, each member singing the story of its own life and death.